We all know that, fundamentally, matter is made up of atoms. We also know that atoms themselves are composed of protons, neutrons, and electrons, and that the protons and neutrons are located in a central region called the nucleus, while the electrons are zooming around in orbit around the nucleus. But is this the best way to describe the electrons around a nucleus, just zooming around in orbit? Is there some other order, some structure to how electrons occupy the space around an atom? Actually, there is some organization to the electrons in atoms and molecules. The organization can be explained by the application of quantum mechanics. They may seem like weird, almost arbitrary rules, but the mathematics of quantum theory requires that electrons be organized in this way. And what we'll eventually see is that the organization of electrons helps us understand the properties of molecules and other matter too. What's interesting, though, is that by understanding this organization, we can actually understand why atoms and molecules behave the way they do. That is, we can describe a lot of modern chemistry just by understanding how electrons are organized. Well, how are they organized? Well, think of a two-story house. Each house has floors, each floor has rooms, and each room has furniture. How do you locate a person in this house? You have to specify the floor, the room, and the piece of furniture they're sitting in. It's sort of the same thing with electrons and atoms and molecules. You have to specify their floor, their room, and the furniture they're in. Only we don't call them floors or rooms or furniture. We have other words to describe the arrangement of electrons in atoms and molecules. One thing is for sure, electrons are not arranged at random, nor, unlike Bohr and Rutherford's simplistic planetary model of the atom, are they in fixed orbits like the planets. Let's consider our house analogy for the atom. The floors for the electrons are called shells. Shells are labeled with a quantum number, an integer that starts with 1. This quantum number is called the principal quantum number. The higher the quantum number, the farther the electron is on average from the nucleus. Also, the higher the quantum number, the higher the energy of an electron in that shell. And quantum mechanics states that the energy of the shell is restricted to certain values. That is, energy is quantized. In shell number 1, the electron has the lowest energy. In shell number 2, it has a higher energy, and so forth. Electrons can move from floor to floor, or from shell to shell, but only if they absorb or emit energy in the form of light or heat. But it has to be the right amount of energy. Let's keep it simple and assume that the energy involved is in the form of light. In order to go to a higher energy shell, an electron has to absorb light, and in order to go to a lower energy shell, an electron has to emit light. In addition, the energy of the light absorbed or emitted must be exactly the same as the difference between the energies of the two shells involved. Different energies of light mean different colors of light. So electrons and atoms can only absorb or emit certain colors of light. This explains why the different atoms have different absorption or emission spectra. You may recall that this is one of the problems that 19th century scientists couldn't explain. Quantum mechanics explains it. Hydrogen absorbs and emits certain colors of light because its electrons have certain quantized energy values. And that means that the differences in quantized energy values are also quantized. Think of a staircase. Not only are the stair heights at certain specific values, but the differences in the stair heights are only certain specific values. For example, a neon atom has electrons with different energies from hydrogen, so the changes in energies and the light involved are different as well. This is why a neon light has a different color from a hydrogen light, or an argon light, or a mercury light, or a sodium lamp. The different elements involved give off different energies or colors of light. The hydrogen atom has only one electron. For reasons we'll see shortly, because of this, the energy of the electron is determined solely by the principal quantum number, by what floor the electron is on. Earlier, we used the analogy of a house to claim the presence of rooms and furniture, but for hydrogen, this isn't necessary. The energy of the electron in hydrogen is determined only by this one quantum number. This is why the spectrum of the hydrogen atom is so simple, and quantum mechanics predicts the exact same expression for the energies of the hydrogen atom that Bohr's ideas did. But quantum mechanics is a better model for electrons because it treats them as waves, whereas Bohr's theory didn't. When there's more than one electron in an atom, there's a new effect. The negatively charged electrons repel each other depending on how far apart they are. This means that even though the electrons may be on the same floor, that is, in the same shell, if they're in different rooms, they'll have different energies. Each individual room is called a subshell. Subshells can also be labeled with a second quantum number called the angular momentum quantum number, because quantum mechanics predicts that the angular momentum of the electron is quantized as well. But for this second quantum number, rather than using numbers to label the value, we use letters. This keeps us from getting confused between the two separate quantum numbers. The first four labels, which are the most common ones, are in order S, P, D, and F. Within each shell, an S subshell has the lowest energy. A P subshell has the next lowest energy, and so on. Because of the mathematics of quantum mechanics, the first shell is limited to one subshell. So shell number 1 has only an S subshell. The second shell is limited to 2 subshells. So shell number 2 has an S and a P subshell. The third shell has only 3 subshells. The fourth shell has 4 subshells, and so forth. Notice the trend here. We can actually predict the number of subshells in a shell. The 25th shell would have 25 subshells, wouldn't it? It's worth pointing out again that this trend is established by the mathematics of quantum mechanics, not because scientists want to make things confusing. For atoms with more than one electron, the exact energy of the electron depends on the shell and the subshell that the electron is in. This is why the spectra of other atoms other than hydrogen are more complicated to explain. But again, quantum mechanics explains this, so it's definitely a better model than Bohr's model. Now let's look at each subshell. Going back to our house analogy, what we find from quantum mechanics is that each room only has a certain number of pieces of furniture in it, depending on the type of room, that is, the type of subshell. In quantum mechanical terms, each piece of furniture is called an orbital. Any S subshell, no matter what shell it's in, has only one piece of furniture, one orbital. Any P subshell, no matter what shell it's in, has only 3 pieces of furniture, or 3 orbitals. A D subshell has 5 orbitals, while an F subshell has 7 orbitals. Again, we see a trend here. So the total number of orbitals in a shell depends on the shell number, which determines the number of subshells, each of which have a certain specific number of orbitals. Each orbital in a particular subshell is slightly different, because it turns out that an orbital in a subshell has a certain shape in 3-dimensional space. The S orbital is spherical in shape. A P orbital looks sort of like a dumbbell. Now, there are 3 P orbitals in any P subshell, so what's the difference between them? The 3 orbitals are oriented in 3 different directions in space, which we can arbitrarily label the X, the Y, and the Z directions. The orbitals themselves are identical to each other, just oriented differently in 3-dimensional space. The D orbitals have the shape of double dumbbells, or rosettes, and the 5 D orbitals in the D subshell also have different orientations in space. In principle, this idea continues into the F subshell, and so on. There's one last thing to consider before we understand how electrons are organized in atoms bigger than hydrogen. All subatomic particles, protons, neutrons, electrons, and other particles, have a property called spin. It's not that we know they're spinning around like a top. We can't even see an individual particle in order to tell. No, it's that they're behaving like they were spinning. So we use the name spin to describe this behavior. Now, different particles have different characteristic spins that can point in certain numbers of directions. In the case of an electron, its spin can point in two and only two directions. We call them up and down, alpha and beta. It doesn't matter. The only thing that's important is that an electron has two possible spin states. In the 1920s, Austrian scientist Wolfgang Pauli proposed the idea that an orbital can only contain as many electrons as there are directions of spin. With an electron, that's two. So each orbital can only hold a maximum of 2 electrons. If an orbital were a piece of furniture in our house analogy, this piece of furniture is a small couch or a love seat, seating only 2 people. This understanding limits the number of electrons that could go into orbitals, into subshells, and into shells. For example, shell number 1 has one s subshell, which has 1 orbital. This 1 orbital can hold a maximum of 2 electrons, leading us to the conclusion that shell number 1 can only hold a maximum of 2 electrons. Shell number 2 has 2 subshells, S and P. The S subshell, like all S subshells, can hold a maximum of 2 electrons. But the 3 orbitals in the P subshell can hold 2 electrons each, for a maximum of 6 electrons possibly occupying that P subshell. Add these 6 to the 2 in the S subshell, shell number 2 can hold a maximum of 8 electrons. In shell number 3, add 10 electrons that can occupy the 5 d orbitals for a maximum possible population of 18 electrons, and so forth. With this understanding, let's see how electrons are organized into shells, subshells, and orbitals for the first few atoms. Hydrogen atoms have a single electron that goes into shell number 1, the S subshell, and the only orbital in the S subshell. Helium atoms have 2 electrons, and both of them can go into shell number 1, the S subshell, and the only orbital in the S subshell. How does this look, the electrons in the 1s subshell and shell combination? Here are some fundamental results from quantum mechanics. The energy of the electron is quantized, and the angular momentum of the electron is quantized, but the location of the electron is not. That is, we don't know the exact x, y, or z coordinates of any electron in an orbital. That's why the analogy of electrons behaving like planets around the sun doesn't work. We cannot say exactly where an electron is. All we could do is map out a region of space where the electron is most likely to be. Rather than calling this an electron orbit, we call this an electron cloud. Instead of saying where an electron is, all we could do is state a probability of where an electron might be. Quantum mechanics reduces our understanding of electron behavior to probabilities, not certainties. Now, if you think this is weird, you're not alone. Even Einstein was uncomfortable with this interpretation of quantum mechanics. But think about it. An electron is a wave, right? And where exactly is a wave anyway? Modern scientists understand that this probabilistic nature of electron behavior is the best we could do at this level. Before we go to even larger atoms, I'm going to introduce a sort of shorthand that scientists use to summarize the organization of electrons in an atom. It's called an electron configuration. Using this shorthand makes it easier for scientists to communicate what shell and subshell electrons occupy, and what happens to electrons and atoms when chemical reactions occur. An electron configuration is just a list of the quantum numbers that the electrons have as they occupy shells, subshells, and orbitals. Most electron configurations only explicitly list the principal quantum number and the angular momentum quantum number, actually a letter, and have superscripts giving the number of electrons in all the orbitals of the subshells. For example, the electron configuration of hydrogen is 1s1. The electron configuration of helium is 1s2. The next element is lithium, which has 3 electrons. We could try to put the third electron in shell number 1, s subshell, and the single orbital of the s subshell, but that would mean putting 3 electrons in one orbital, and a single orbital can only hold 2 electrons at most. Nor can we put that third electron in another orbital in shell number 1. Shell number 1 only has 1 subshell, which only has 1 orbital. No, shell number 1 is completely filled. It cannot accommodate any more electrons. That third electron has to be put in shell number 2. Shell number 2 is farther away from the nucleus than shell number 1, so when going from helium to lithium, the size of the atom makes a big leap. Lithium atoms are about 30% larger than helium atoms. Being farther away from the nucleus, the third electron is much easier to remove from a lithium atom than the first or the second electron. This is what we mean when we say that the electron in the second shell has a higher energy than the electrons in the first shell. But the second shell also has 2 subshells, an s subshell and a p subshell. Where does this third electron go? Experiments show that the s subshell is always lower in energy than the p subshell in any given shell. So that third electron goes into the s subshell of shell number 2. So the electron configuration of lithium is 1s2, 2s1. Because the 2s shell-subshell combination can hold up to 2 electrons, when we go to the next element, beryllium, that fourth electron also gets a 2s label, and the electron configuration of beryllium is 1s2, 2s2. For the next element, boron, with 5 electrons, we needn't go up to shell number 3 yet. That's because the number 2 shell has a second subshell, the p subshell, which can hold a maximum of 6 electrons. The p subshell is slightly higher in energy than the 2s subshell, but not as different in energy as the 1s subshell. As we progress through the next 6 elements in terms of electrons, boron, carbon, nitrogen, oxygen, fluorine, and neon, each additional electron in the atom contributes to filling that 2p subshell. For the first time, though, we're filling a subshell that has more than 1 orbital. How do the 6 electrons distribute themselves among the 3 orbitals as they're filled? Experimental evidence, primarily measurements of magnetism, show that a single electron occupies each individual orbital before a second electron pairs up with the first one in one of the orbitals. It's similar to strangers filling seats on a bus. Each bus rider selects a seat to sit in by themselves until all the seats have one rider. The next rider, though, has to sit with somebody else. And so it is with electrons filling orbitals. Eventually, however, we get to the element neon, and the 2p subshell is now filled. We have an electron configuration of 1s2, 2s2, 2p6. Now we have to move up to the shell number 3 because shell number 2 only has 2 subshells and they're completely full. Going to the next 2 elements, sodium and magnesium, we put electrons into the 3s shell-subshell combination, and then with the next 6 elements, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, we put electrons into the 3p shell and subshell. So far, in case you're not keeping count, we've been able to accommodate a total of 18 electrons. At this point, for the next element, potassium, we might expect the electron to go into the 3d subshell because shell number 3 has 3 subshells. But this isn't what happens. Experiments show that this next electron, the 19th one overall, goes into shell number 4, the s subshell. What's going on? Well, it all has to do with energy. It turns out that putting an electron into the 4s subshell gives an atom that is lower in energy than if you put that electron into the 3d subshell, the third subshell of the third shell. Recall the importance of energy in the behavior of matter. One of the most general concepts in science, and an essential concept in understanding the nature of matter, is that when left alone, many systems tend to adopt the lowest possible energy. That's why a rock rolls down the hill. It's trying to achieve the lowest gravitational potential energy. Same thing for when you drop something and it falls. Lowest gravitational potential energy. Why does a compressed or an elongated spring spring back to its normal distance? Minimum energy. Well, it's the same thing for electrons and atoms. The overall atom, with all of its electrons, wants to adopt the lowest overall energy. It turns out that in order to do that, the 19th electron in potassium goes into the 4s subshell instead of the 3d subshell. We speak of the electron configuration for potassium as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, not 3d1. For the next element, calcium, the next electron also occupies the 4s subshell, and now that subshell is full. Now the next electron, our 21st electron, goes into the 3d subshell. The 5 orbitals of the 3d subshell can accommodate a maximum of 10 electrons, and over the course of the next 10 elements, the 3d subshell is filled. Now that the number 3 shell is completely filled, electrons have no choice but to go into the 4p subshell, which covers the next 6 electrons, and now we're up to a total of 36 electrons. But now the break with the pattern is set. Although there is a regular ordering of filling the shells and subshells with electrons, the order now depends on the shell and the subshell type. Frankly, it gets a little messy, but the trend has been all mapped out, and the electron configurations of the remaining atoms are well known to scientists. In a simple way, these electron configurations illustrate how electrons are organized in atoms. Well, what about molecules? A molecule is 2 or more atoms connected together. So how are the electrons organized in molecules? Actually, they're organized in a way very similar to atoms, into orbitals, called molecular orbitals. In the case of molecules, though, the orbitals cover the entire molecule. They don't just stay on any one atom. We can think of a molecular orbital as being formed from combinations of atomic orbitals from the atoms that make up the molecule, which in turn makes up matter. Well, that's not always strictly true. Many molecular orbitals are virtually identical to the original atomic orbitals. But technically, they're no longer atomic orbitals, they're molecular orbitals. One rule is that a molecule has as many molecular orbitals as their atoms have atomic orbitals to hold their electrons. For example, when we make a molecule of H2O, water, from 2 atoms of hydrogen and 1 atom of oxygen, we need to count the atomic orbitals. Each hydrogen has 1 orbital for its electrons, while the oxygen atom has electrons in a single 1s orbital, a single 2s orbital, and the 3 2p orbitals, for a total of 5 orbitals. 1 plus 1 plus 5 equals 7. So the water molecule needs 7 molecular orbitals for its electrons. And another rule is the same. Each molecular orbital can contain a maximum of 2 electrons, as long as the 2 electrons have different spins. If you were to look at diagrams of the molecular orbitals, you would see that some of them resemble the spherical or dumbbell or rosette shapes of individual atomic orbitals, while others cover more than one atom, sometimes the entire molecule, which is why they're called molecular orbitals. Because the water molecule only has 10 electrons, only the 5 lowest energy orbitals have electrons in them. The other 2 are present but empty, just like what sometimes happens in atomic orbitals. One of the difficulties with molecular orbitals, though, is that they're different for every molecule. The molecular orbitals have to conform to the shape of the molecule, and because every molecule is a different shape, molecular orbitals are unique to each molecule. This makes it difficult to make a lot of general statements about molecular orbitals. Investigating their properties is a focus of a lot of research among scientists because the properties of molecular orbitals tell us a lot about the chemical and physical properties of the substance. One interesting property that molecular orbitals give some molecules is demonstrated by the molecule benzene, which has the formula C6H6. The benzene molecule has its 6 carbon atoms in a ring, and the molecule has a shape of a perfect hexagon. If we take a look at one of its molecular orbitals, we can see why. One of its molecular orbitals goes all the way around the ring, almost in a circle. The word we use to describe this type of electron behavior is delocalized. What we've discovered about delocalized electrons is that the more they're delocalized, the lower in energy, the more energetically stable they are. As a molecule, benzene is rather unreactive towards other chemicals, and this delocalization of the electrons is used to explain that. Because it is so unusually stable, benzene typifies a class of compounds called aromatic compounds. The word aromatic was originally used because benzene and similar molecules were, well, rather stinky. But now the word aromatic has a new scientific meaning. It describes compounds that are more energetically stable than expected due to the delocalization of electrons in rings of atoms. As I mentioned, benzene is a typical aromatic compound with a single ring. Other aromatic molecules can contain more than one ring, and so are called polycyclic aromatic hydrocarbons, abbreviated PAH. Certain PAH molecules are formed in the charring of meat when you barbecue outside, which has led to some health concerns because some PAH molecules are considered carcinogenic. Aromatic molecules are not limited to hydrocarbons, which are molecules that contain only the elements carbon and hydrogen. The elements nitrogen and oxygen are also commonly found in aromatic molecules because the atomic orbitals of these atoms are similar to carbons. The original model of electrons and atoms was called the plum pudding model, so called because the English scientists who proposed it thought the electrons were distributed at random in space, much like the raisins, which are called plums, in this English dessert. However, with the fact that electrons behave like waves and with the development of quantum mechanics, the plum pudding model wasn't feasible. Instead, electrons have quantized energy and angular momenta, and because of the mathematics of quantum mechanics, we find that electrons are grouped into shells, subshells, and orbitals. This electronic structure gives atoms and molecules their electronic properties, which in turn strongly influence their chemical and physical properties. Our house analogy for the electronic structure of atoms is now complete. It doesn't work quite as well for molecules, but that's okay. Molecules and molecular orbitals are built from atoms, So I suppose we can consider a molecule like a small city, a collection of houses that have floors and rooms and furniture. Each molecule is different, just like every city is different. But it's these differences that make learning about the nature of matter so much fun. Thank you.